Ми представува честито задоволство да ја отвориме седмата сесија на вебинари, кои што ги организираме во рамките на EuroCC проектот EuroCC for C. Така што денеска ќе имаме две презентации. Првата ќе биде на тема LLM routing, Intelligent Model Selection for Optimized AI Systems со страна на професор доктор Игор Мишковски, а потоа ќе следува со својата презентација професор доктор Сашо Граматиков. Нема да доложам повеќе, Игор повели своја презентација.
Hvala, Đorđe. Zdravo na sita. Како што кажа Ѓорѓи, мојата презентација денес ќе биде LLM рутирање. Ќе направам еден свич на англиски, ќе презентирам истата на англиски. So, what's the agenda about? What I will speak about? Just a second, it's a little bit slower. Okay. So the agenda is, first I will make an introduction to LLM routing, so some definition, what are the benefits and the core concepts. Then I will speak about different routing strategies, like either we do it in a pre-generation or post-generation, and some classification of the possible routings. So I will present later on the research, what is the state of the art in the research, some of the industry solutions that we have, what we have for benchmarking and evaluation of the routers, and what are the some of the challenges, drawbacks, and future directions that needs to be developed in order to have optimized intelligent AI systems. So I will start with the definition of LLM routing. So what is an LLM routing? It's a simple definition, is a component that directs user queries or prompts to the most suitable model from a given pool of LLMs or candidate LLMs in order to optimize the trade-off between the performance and the cost. Of course, this can be a longer list. It can be also latency. It can be green energy or being green and stuff like this. However, it's an optimization function, and the formal definition is that given a query or a prompt and given a set of models, we want to maximize some kind of scoring function. And given a budget constraint, so it means that the cost should be less than this budget constraint. The cost of executing a given query on a given LLM should be less than a budget constraint. In this way, we optimize the quality, we minimize the cost, and we, of course, as I mentioned, we can reduce the latency, which is quite important in production systems. What is the on the right side, we have the routing flow, we have the user query, and the LLM router should decide which is the best LLM for a given query, given prompt, given context, given data, what is the best LLM in terms of all the three things which I mentioned. Why does it matter? Because here are some results from the research state of the art. So we can achieve, for instance, cost difference between models 50 times less or even 100 times. One comparison is Claude 3 Haiku versus Opus. You can see the difference in the generating million output tokens. So not all the queries deserve to be executed on Opus. Some of them can be, Haiku is enough, or depends on the query. So one strategy is to have always the best model, which we always, most of us is doing this, like having the best model, but we introduce high cost. If we do the small model, we have a low quality, so we have to have the best of both worlds. I did some research together with Maria Stojčeva about the Open Router. This is the data from Open Router from July to October, and we can see, we just analyzed if there is an evidence for needed LLM routing. So you can see that the weighted entropy starting from July to October increase double. So it means that, people are not choosing always the same models. They are like dispersing between the models. In the meanwhile, the token volume doubled. So it means people are using more and more Open Router as a platform for AI. Another thing we analyzed is that we analyzed 37 models across different 12 tasks. They classify the task in different categories, and you can see that the hypothesis was the LLM model is chosen at random, but you can see the the chi-square test showed that it's actually not a random connection, and also the Cramer's value, which is not one, but it's still strong. So it means there is a strong correlation between what the user wants, that is the task, and the LLM they choose. So it means we have the real world evidence, and the user are selecting the LLMs based on their tasks. For instance, one of the most differentiating tasks was programming tasks. So people concentrated more on the specific code-specific models. Also translation task, they use multilingual models, whereas some of the marketing and legal, it has a high entropy. So it means there is no the big winner there. So the the inference is choosing the LLM is not so, let's say, we have the best LLM for legal and marketing, but they use different models. This is just real evidence from the LLM routing. There are two main categories of routing. So one is the pre-generation routing, and the other is the post-generation routing, or what I will focus more here is the pre-generation routing. Whereas there is another, let's say, strategy that is a cascade strategy. So I will explain both of them. So the idea with the pre-generation routing is that we route before generating any response. So there is no response. We have the task, we have the query, we have the prompt, we have all the context that we need, and we select the best LLM. When I say best, the optimal, I mean the optimal LLM for executing this task. Of course, this is a single LLM call, so it means it's a low latency, predictable cost per query, and but it requires, this is the drawback, it requires quite accurate complexity prediction. So we need to have some kind of either traditional or generative models to predict what is the optimal LLM. The second let's say niche is the post generation, the cascade niche, which is first we have a response. It's like a cascade. We have a response usually from a smaller model, and then there is some kind of evaluation if the response is correct or not. And then we escalate. If the response is not good enough, then we escalate to a better model. Let's say we have a dual model, so we go with a more expensive model. Of course, it's quite evident that this introduces more latency and more cost if there is escalation. Usually what they do is either have some kind of small fine-tuned model that is trained to predict whether the response matches what the user wants, which is quite tricky, or the other way is to use another LLM to evaluate the response quality, which is again latency. So that's why I will not focus on cascade routers, but pre-generation routing. So what kind of implementation strategies we have? We have four, just to have a pen. We have the similarity based, which is based on semantic similarity. So I will go into deeper later on. So we have the query similarity, clustering, or preference similarity, like three different subclasses of similarity based. Then we have supervised approach, which is quite the opposite of the first one. So first one is either weak supervision or unsupervised, whereas in the second subclass we train classifiers on the domain, on the task type. Usually we can classify what the user wants in, let's say, a dozen of tasks. Either is some kind of rewriting, either is summarization, it's a coding task and stuff like this. So it's more or less dozen of tasks. But also we can with the classifiers we can inference the complexity of the query. So it's like some kind of number that tells how complex is the query. And here is also, we can use the knowledge graphs as some kind of representation between LLMs and query. I will go deeper. Usually what in the literature, what they use is either ModernBERT or DeBerta, like a classifier. They're using this for training the supervised subclass. The third subclass is reinforcement learning. Of course, there is a known issue with the reinforcement learning. It's difficult to have a stable state at the end. What they do is either the simplest one is the stateless the bandit algorithm. Then they have they use the state-based where they, sorry, where it's not only one the winner, but depending on the context, you are choosing the right strategy. So it means it's state dependent, and the most complex is the reward inference. I will speak about this later, just to have the four main classes. And the fourth one is generative. So it's actually use some kind of either LLM information or use another LLM to make the routing decision. So it can be prompt based, like, yeah, okay, I have this query and ask an LLM where to route it. This is the simplest one. We can use the token probability. We can use the cumulative token probability, like independent probability, or we can fine tune another LLM for just measuring the probability of yes and no tokens at the output of the LLM. We can somehow make a decision. So these are the main four classes: similarity based, just to summarize, the supervised way, the reinforcement learning, and the generative way. So we are going now deeper. We are going in the similarity based. The core idea, as I mentioned, is to route queries based on how similar they are to the past queries we had, where we know which model performs best. So we have to have some kind of data benchmark the company has to have in order to do this similarity-based routing. So the first, as I mentioned, the first subclass is query similarity. What is the idea here? The simplest way is nearest neighbor, k nearest neighbors, or maybe use contrastive learning, so we know to differentiate, the best from the strong from the weak model. So to have integrated the contrastive learning. The second subclass, the clustering. So quite straightforward also. So two-stage process. First, we identify which semantic cluster a query belongs to, and then route to the model that based on historical data, and then route to the model that historically performs best for that cluster. So it means like having a cluster scoreboard. It's also quite simple. One representative here in the research, which I did, is UniRoute. So what is good about it, that when you introduce a new model, you don't have to recompute everything. You can put this model, calculate only for this model the inference from the history and put it in the scoreboard, in the cluster scoreboard. And the third subclass is preference similarity. So this it's like we have chatbot arena where we have human preferences, like I like most this, better this than this. So it means you have some kind of preference from the user. So we can use the statistical model for ranking from pairwise comparison. So it means we can estimate the probability that the model A will beats the model B. So it's quite straightforward when we have the data from the router arena. In this way, this is called the Bradley-Terry model. So this is actually in the route LLM, which is let's say research paper about routing. They introduced the preference similarity, and of course, also they when they build with Bradley-Terry algorithm, when they beat this, when they estimate the probability, they also do a weighting from the new query comparing to the similar queries in the past. So they have also the semantic connection between the new queries and what they have in the data. In this way, they make a function that scores that gives which LLM is best for the new queries. So this is the first group. The second group, the core idea is to train classifiers on label data to predict which model will perform best. So we can. Here is one representative. It's domain classification. So the simplest thing is like, okay, it's a domain coding. So just select the best model for the coding. It's quite straightforward also. So what they found out is that performance drop from specialized domains when you have queries that are quite specialized to a domain is good. But when you have like general queries, then the performance drops quite a bit. Then there is the second subgroup of the supervised routing is the complexity inference. So it means as to measure the performance gap between a small and large models compared to the reference answer, and they use usually the BART score here. So they have the generated response, they have the reference response, and they measure the BART score between the generated and the reference response. And if there is you have the generated response from the weak and generated response from the let's say the strong model, and if they just do they shrug them and see if the score is below some threshold or above some threshold. So it means go with the weak model or go with the strong model. Then the third approach, the third subclass is knowledge graphs, or I will say better GNNs. There is a paper, I think this year, about using GNNs for this kind of model routing. What is the idea? We can easily represent the task, the queries, the LLMs. The tasks are not necessary if you don't know them, but if you know them, it's a good thing. So you can represent like a bipartite graph. You have the LLMs on one side, you have the queries on the other side. So the edges are actually some kind of performance relationship between the query and the LLMs. And at the end, they use the graph attention networks or any other GNN architecture, convolutional networks, to make an inductive prediction. What is good about this is that they generalize, in theory, they generalize the GNN generalize, so they can generalize to new LLMs without retraining or new type of queries without any retraining. But this is more theoretical than practical. I mean, we shouldn't rely in production on this. And the third type of routing is reinforcement learning. So the core idea is to learn the policies through interaction and feedback, so to optimize for the reward. The rewards can be the correctness, the cost, the latency, emission, or whatever we have as a data. They're in order of complexity. We have three of them. One of them is the simplest approach is to use the stateless. So stochastic learning automation. This is pick LLM. You have at the bottom, you have some representative. The representative is pick LLM. So what they do is actually they track the probabilities of selecting each model, and then sample randomly based on this probability distribution. Higher probability, more likely to be selected. And the update mechanism is that they adjust the probabilities up or down. The good result is that they increase selected model probability, but decrease the others, of course. What is the problem is cannot adapt to contextual change. So it means learns only the best model overall. So in this way, we don't have any context. So that's the major drawback of the pick LLM. Then we have the second subclass, which is the state-based, and the state-based. In the state-based, we incorporate the context into routing decisions. So it means that different contexts, different situations will produce different optimal models. So it means it's not one model is the best, but we have for different contexts, we have different model. Here is the meta LLM is contextual multi-arm bandit approach. And what we have as a state, we have the query embedding, the task type, if we have it, and we have the user history. We can also introduce the user history. In this way, the selection model actually is based on picking the best Q value in the reinforcement learning, but there is also exploration component, and it's not so it's epsilon greedy, and the update estimated reward value for the selected model is the old value, the old Q value, plus the learning rate multiplied by the actual reward minus the old value of Q. That's the state-based, the contextual multi-arm bandit approach. And we have the third subclass, which is the reward inference, which is, I must say, quite complex compared to the others. So it's here is the representatives, the router R1. It's a multi-round sequential routing. So it means that there is a trained model that makes a sequential decision. There is a involved sequential decision process where the model thinks, analyze, and reason internally. Then it divides the query in several subqueries, then call different LLMs for the different subqueries it has, and combine the information from all the LLMs and measure the outcome, the final answer. If usually they have, when they train, they have the exact match as a correct answer. So the reward is based, it's all a 0 or 1. The cost, there is the cost involved. So you can see the router R1 formula through reinforcement learning is actually using this reward. So this is the format. If the model does not produce the format like I mentioned here, the thing, the route, and the aggregate, then the reward is 0. So it means it has to produce this format. Actually, it's -1. Sorry, not 0, -1. 0 is if the outcome is not correct and the cost reduces, penalizes the final reward R. So these are the ideas from the reinforcement learning approach. Then we have the fourth class is generative routing. We have here 4 different approaches. I will focus most on the fine-tune approach, how to fine-tune a smaller LLM to make a decision which LLM to choose. But of course, the simplest way which we can think about is to have a prompt, like nest everything in the prompt and ask the LLM which is the best LLM to route for a given query. This is the most silly, most simple approach. Another approach they use is token probabilities. So they measure the probability of the token, and if the margin between the top 1 and top 2 token are quite close enough, it means that he's not so sure for the response. So there is low confidence, and they escalate to a larger model. The fine-tune LLM, I will speak later. So I will just keep the red one. And the sequence probability, instead of looking just one token uncertainty, they have the whole sequence probability, and they just they use the cumulative confidence, the logarithmic cumulative confidence across the entire generated response. They normalize by the number of tokens, and if it's close, this sum is close to 0. That means the model is pretty certain that that the answer is correct, so he doesn't have to escalate. Okay, so it means this model can answer by itself. Okay, which is actually doing, if it cannot, then it escalates to a bigger model. If not, it gives the answer by itself. It doesn't have to be another model that gives the answer. So it's more like cascade routing. So yeah, okay, these are the just to sum it up until now, what we passed the 4 main different routing implementation strategy. The simplest one, similarity based, which works quite nice in my experience. The supervised way, which can be also seen as maybe addition to the first one, like having additional context about the query, like the complexity, the domain classification if we don't have it, the reinforcement learning, which can be offline, online if we have the tools, and the generative using another LLM. And we had so what are the solutions? Some of them I mentioned before. So we have these are, you will see 2024, 2025. This is the state of the art in the research. So just for a route LLM, it's paper and a GitHub repo where you can use this router. They have 4 different strategy. They're using similarity weighting ranking. So it means it belongs in the first class, but also they introduce they use also matrix factorization for new queries. So it's collaborative filterings, like queries are the users, the new queries. So they use also this, or they use also supervised they have, different three types. You can choose what kind of router you want. You can use a router LLM with similarity weighted. You can use with matrix factorization, or you can use with BERT classifier, which is it's a mix. It can be in a second class, which is the supervised. Graph router, I will speak in details after this. So I will. Okay. I will speak about this later. We have the router R1, which is the reinforcement learning multi-round routing. This was with the think, analyze, and this is this approach, just reward inference, which was the complex one. Then we have the mix LLM, which is mix LLM. So the idea here is that sometimes what they introduce in the mix LLM is they have dynamic streaming routing. So all of these previous routers which I mentioned are not streaming. So what is the idea? Maybe the queue or the requests are going too much to one LLM. So this takes into account also the queue that is waiting to be executed on a given LLM. So it's like a real-time in the reward, they have also this latency as a parameter. So this is the main thing about the mix LLM. Then we have X router, which is a end-to-end learned routing with explicit cost optimization. It used decoupled clip and dynamic sampling policy optimization. So it means decoupled clipping. There are three different things. So it means there are different clipping ranges for increasing and decreasing probability. So it's asymmetric. So it's not, the good models go the same way as the bad models. So there is this decoupled clipping. There is dynamic sampling. So it means some of the queries are hard, some of the queries are simple. So when the query is hard, it means that it generates more and more requests to the LLM, because it doesn't mean that an LLM will give always the same answer. So he maybe has some trouble, say, answering giving the result for the query. And there is no critic network in this approach, so uses group relative advantages, which is more stable for large training. And the third one, which I will present two routers which I used, but so it's a graph router and generative router. I will not present uniroute, but uniroute actually is similarity cluster based. So it's the first class, second subclass, which is the similarity based with the cluster based approach. So actually generalized to dynamic LLM pools. It uses k-means clustering, learned cluster mapping, and if the LLM is unseen, if it's a new LLM, you don't have to recompute everything. Just you need to recompute for this LLM the statistic, which is the cost, the score, and the latency, and just put it in the clustering table. So mainly this is the key academic solutions. As I mentioned, I will speak shortly two representatives. One is the graph router, and the other is capability instruction tuning. I will not go. I noticed that I'm at the middle of the presentation. I don't have so much time, so I will skip some of the slides. What is the idea? We have the tasks, we have the queries, we have the LLM embeddings. We make what they do in the paper. They make a feature align model. Then do a concatenation. So they have the bipartite graph of the query nodes and the LLM nodes. Then they use the two-level graph convolutional network. So it's layer 1 and layer 2. They use the edge attributes. They use edge attributes as an edge attributes. They use the cost, the effect, which is actually the score, which is how good the answer was. Can be 0 or 1 if it's an exact match, or can be LLM as a judge, or whatever it is, or a human evaluated effect, and the task score. So it means it also takes into account how on the given dataset, let's say MMLU dataset, how LLM was good at a given task, like science, maths, physics, these kind of tasks. based on this two-layer graph convolution network, they make an edge score prediction and they make per query classification. So it means that if they have 12 LLMs, I had 12 in my environment, so we have a score for each of the LLMs, and we select the best LLM for the given query. As a loss function, we use the cross entropy loss here. So this is actually, if you go back, this is the generative routing. No, sorry. This is the knowledge graphs like a supervised GNN, like a supervised learning, because it belongs to this supervised routing. Sorry. The second thing, which was quite okay. Here are some results from our research that we did. So this is actually a data set that was selected from MMLU, just to find that, I will see the data sets. I think human eval, MMLU, and GSM8Q, and it was like selected random samples. And what we found out is that here are the different routers. So you have this is the Pareto optimal curve. Okay, this is the oracle who knows what is the optimal model to select, and these are actually the individual models, how they behave on the data set, on the test data set. What is the finding here is that the GNN router, it's maybe the best around the score, but a simple leaderboard on this data set actually performs quite good. So it means the GNN, it's better, but the score is not so different, and the cost, the leaderboard, because it introduced also as optimization function in building the leaderboard, is actually making a less cost than the GNN router. You can see the best individual model for this data set the score was 0.5, and the score, if you use the best model for this data set, you will pay per 1 million queries similar like we had, because we didn't have 1 million, but we approximate, you will pay around 4K. Whereas if you use the GNN router and leaderboard, you will pay 10 times less, and you will get the same cost, the same score, or even better a little bit, but it's not so significant, let's say. The second is the generative routing. What we have is each of the LLMs is represented with a capability instruction. Capability representation? Sorry. So what is a capability representation? Is actually a text that describes the LLM. I am good 70% at math. I am good 50% at coding. I am good. So it's like you have a data set, and then you measure the score, and based on this score on the data set, you build this capability representation. This is the here. I don't know why I cannot zoom. Just a second. Let's see. Okay, this is the capability representation. Then we have the user instruction, which is actually the prompt that we need to answer. And then we have a performance inquiry. So it means we are predict whether the model can handle this instruction by indicating yes or no. So we have these three parts, and then we have, because the capability representation, we need to encode somehow. We used E5 large as a capability encoder, and then we use the connector. They use the connector in the paper, but in our implementation, we just re-implement the things. We use the connector that actually connects the exit output of the encoder and make a concatenated capability instruction, which is consisted of the output of the connector, of the user instruction, and the performance inquiry. So the idea is to train here was the Fit3 Mini, the Microsoft Fit3 Mini with the LoRa. We train it with the LoRa just to see we train it on the final score. So it means like we measure the probability of given the concatenated representation, that is the exit of the connector, which is just a representative of the capability representation, the user instruction, and the performance inquiry. We measure the probability of of the token yes. So this is like actually is a two-stage process. First, you train, you freeze the capability representation and the LLM and just do the connector training, and then in the second stage you just make the whole tree training. So you train the capability encoder, you train the connector together with the LoRa adapter, for the LLM. Although you can, if you have a smaller LLM, then you can fine tune the LLM. However, the results were not so good as the claim in the paper, I must admit. Okay, this was about the research state of the art. Then on the other part, we have the industry. So the idea is what the industry is providing to us, like to have cost reduction and cost and latency reduction, and to have let's say similar performance comparing to the best model. If you go to Azure AI Foundry, you can always deploy the model router, which is a quite simple model router. It's a deployable chat model that intelligently selects the best LLM for each prompt. So what it's doing in the background, it evaluates the complexity of the prompt, the cost and the performance of the prompt. You can when you deploy it on Azure AI Foundry, you can select three strategies or modes. You can go to balance, which is the default. You can go to quality first, and you can go to cost first. So it means either you are between the quality and the cost, or you want to be more about the cost. You cannot change this number. So it's like three radio buttons. You just select one of them. It's a single. What is good? It's a single deployment. It supports not only OpenAI family, but also which was from, I think, November 2025, 18th of November. I think it's Anthropic is there, so it means you can also use Claude Opus on a Haiku 4.5. So it means you have 18 models in the latest version of the model router that you can use. What is the images and audio and prompts is not supported by Azure AI Foundry model, neither by Azure, neither by AWS, GCP. I'm not sure. I didn't work with GCP, but you cannot, when there is an image and you ask, what about this image? The image is just forwarded. I mean, just the prompt is evaluated, which is what is in this image, and not the image itself or the audio recording. So it doesn't, we are still far away from selecting the best model for the best image or best transcription or whatever it is. Then is the AWS Bedrock Intelligent Prompt Routing. It's quite similar. The only difference is that it routes prompts within a model family. So it means you have to stick to the model family. You can use also Metalama and Amazon Nova or Anthropic Claude. Okay, so it functions on the similar way, analyzes the prompt complexity and make auto routing to, let's say, Haiku or Sonnet. Here are some numbers which they claim they achieve with this. Okay, so you can select in the configuration some kind of threshold. So it means if this threshold is not satisfied, there is a fallback model selection, which can be the default model they provide, or I'm not sure about the default model, or some custom models. So they support English text only within their family. What is another interesting, let's say, production router which we can use is VLLM semantic router. So what they provide is here is one API call to the VLLM endpoint. So it's chat completions. Yeah, I want to select the model. This is how it looks. Model, here is the role, here is the content, and blah, blah, blah. But for instance, here is another one where what is the issue here is you assume that GPT OSSS is the best model. This is what you assume and you are calling this model through VLLM. But if you just put model auto in the call, the VLLM semantic router based on the query will not only select the best model, but also for that model will select the maximum tokens. This is like the second optimization they do. and what is the reasoning effort it needs. Okay, so it means that if it needs some built-in, some of them have built-in reasoning, some of them has this explicit chain of thoughts, but they actually enforce, depending on your query and context, they automatically select this. So it means that here is an example, just to yeah. So it's like, okay, maybe GPT or SSS needs less number of tokens and the Qwen tree needs a little bit more number of tokens. So this is the difference between what Azure and AWS is offering. So what they claim is that so it's like previously without the semantic router from VLLM, you see now the call. It's just this. Okay, and what you get is the best model because the complexity is the high, the reasoning effort is high, and the domain is math. Another thing, this is like a high-level language, so it's like comparing assembly to a high-level language. This is what we had to do before. The Gen AI developers has to set everything, all the parameters, also the reasoning, what kind of reasoning should be low, should be medium or high, depending if the model supports this, like Qwen3, DeepSeek, and GPT or SSS. They have three types of reasoning. Also, the token limits, how many maximum tokens to put, but the idea of VLLM semantic router is to select also this kind of, let's say, a second optimization problem, which is the token budget problem and reasoning granularity, let's say, from low to high. How they implement their semantic, this is more about implementation. What is good about this is that it's a Rust core, so it means they use the Candle framework. It's a Hugging Face Rust native ML framework. It's a fast. There is no Python overhead, so it means it's the fastest as it can be. And also on the other side, in the core architecture, they use the Hugging Face tokenizer, but Rust-based tokenization for the speed. So it means the Rust core, it's high performance. They use high performance classification. For the ML component, they use the modern BERT. I think it has 8K context, so it's quite better than the previous BERT versions. They use it for the intent classification. Okay, what they use as a classification for the incoming prompts to classify to the intent type. Okay, this is not so important for maybe for this lecture, but they use cloud native integration through Envoy. So it means that allows router to intercept the request and to at the proxy level before they hit the LLM backend. So it means they support Kubernetes service mesh deployments. Okay, this is the idea. It's a quite production ready open source solution. Yeah, in the interest of time, I mentioned some of the things here. So what they claim is that, here's the claim they achieve with the semantic router compared to the direct VLLM. So it means without the semantic router. And actually you have here you have just auto. You put just auto, and here they try to tweak all the parameters, all the max tokens, the reasoning effort and stuff like this. And they couldn't pass accuracy of 89 because they didn't check all the possibilities for the given prompts, but they were like fine tuning, trying to find the best parameter settings for LLMs, and they achieve 3 times better accuracy when they use the semantic router. This is what they claim. The response time was faster when they use semantic router, and the token usage was like 40% less. So use this. I have used this VLLM, and it's quite nice. The semantic router as implementation. It's quite fast. Another thing, another player in the market is NVIDIA. So what they offer, it's not so let's say Rust based, but they offer a multi-head, the Berta model for classifying prompts across 11 task types and complexity dimensions. What is a complexity dimension? They have a not so big data set on which the Berta is trained. It's some K thousand, 1 to 2,000, I think, samples. So they train, they have annotated how creative the LLM should be, what is the domain knowledge it should have, if the context is needed or not, what is the reasoning capabilities that they need, are there some constraints in the query, and if there are few shots in the query. So based on this, the Berta model for a given query gives you this 6-dimensional vector. And also they provide task types. Either is an open question and answer or closed question and answer. Maybe it's a summarization, maybe it's a coding, maybe it's a translation, which is just, I think, rewrite task, brainstorming, some kind of extraction. And another thing, so this is the prompt task and complexity classifier they offer, and they offer the domain classifier. They have 26 domains like finance, like math, science, business, technology, and they have similar the Berta version 3 model classifier. One maybe problem is the max tokens is, so you cannot go, I mean, you can go with the bigger prompts, but they are cut to 512 tokens. So it means you're limited in the number of tokens. They have the full deployment framework. So they use the NVIDIA inference microservices. They use the Triton inference service using the NVIDIA inference microservices. And it's a custom solution that you can build for the routing. So depending what you need, you can put also PII, personal information identification inside. You can put trying to find if it's a jailbreaking and stuff like this. So they have this kind of models that you can connect all of them and make the right decision. So about the benchmarks and dataset, they are not all here, but for instance, you have just I will read them, the MMLU dataset, which is like A, B, C, D, so multiple choice. You have the correct answer. Then you have the multi-turn conversation benchmark, where they use LLM as a judge, which is something which is not so good, let's say. We have the grade school math. We have the human evaluated code generation benchmarks. This is about the evaluation benchmarks. About the router specific resources, for instance, we have a router bench where we have a lot of inference outcomes from a different LLMs and absolute labels. So it means if you plan to implement a new router, so you can use this router bench, you can use router eval or router arena, which is quite new. You have a link at the beginning. There is actually also a leaderboard among the routers. So it means for a given benchmark, which is the best router, I think Azure is the second place, even though it's simple. Maybe later on, if I have time, I will show. Whereas the GNN is on the 10th place. It was yesterday like this. Then what are the metrics which are usually used? So it's cost to reach. Okay, maybe this is a little bit old, GPT-4 quality, but it's how much cost how much you will spend in order to reach 80% of the GPT-4 quality. Then is the deferral curve, where we have a visual plot showing the quality cost trade-off as you route more queries to the stronger models. So it's something like this. Okay, so you go 100% to the best model. So it means you make this deferral curve. Then what is connected area under the deferral curve? So it means the bigger the area here, the better the router it is. And there is a cost to match some kind of baseline quality. So it means a baseline quality you can define, maybe a random is a baseline quality for, you can define what it is. So what is reported throughout the literature is that we can save 2-3 times with the router. So we spend 2.5 times less money, depending on so this is a cascade. This is on this data set. So we can have inductive supervised learning. So it means we don't have to rebuild the router whenever we have a new model. So it means the GNN, this is the additional pros of the GNN. So it means it can easily induct which is the best, if this new model is the best for a given query. Okay, that's it. So what are the key insights? Preference-based method outperforms classifiers. graph-based approach generalized to new LLMs. Sometimes a simple static leaderboard can solve the case, and it's quite simple. You don't have to do generative router or GNN router. So sometimes it works. I mean, it works maybe not as this kind of models, but it reduces the cost. Of course, everybody's benchmarking on a data set, so it's not so objective, let's say. And the results they produce are valid only for that data set. Yeah, results vary by benchmark. Real world distributions may differ, so the benchmarks are not the representation of what we are actually asking on our open router. There is no single best router for all classes. This is okay. What is about the yeah, I will just finish in few minutes. Yeah, in 2 minutes. The industry solution comparison, we have the Azure, we have the AWS, and we have the NVIDIA. I mentioned some of the things. I mention that for the deployment, this is a managed service. This is a serverless, so you need to provide the Amazon resource name, whereas this is the NVIDIA is the self-hosted, so you have a freedom to do what you want. Okay, I will go to the final slide. What are the current challenges? Still, the GNN is promising for the generalization to new LLMs, but in theory, in practice, we know that it's not the case. I mean, we need a lot of data to have this. There is no standardization in evaluation, so it means everybody's doing what he wants and selects the data set and reports the results in a different way. So there is no standardization. Nobody's taking account because nobody's giving the data about the environmental impact. So OpenAI has a big environmental impact. So it means we have to know also this data, because I think this is the most important router who will take into consideration the impact on the environment. Most researchers focuses on chat QA, but we don't have complex pipelines like including MCP tools, agents, and then to have this kind of selection. So it means a bigger context given to the current state of the agent of the call. Future directions. So yeah, multi-round routing. So the approach of router one, where we have sequential model orchestration for complex tasks, they actually started now. It's quite new. We have to have online learning. If we have reinforcement, we have to have online learning because there is a new version of the model. We have to there is a data drift. Maybe the users are asking different things in the company. Agentic routing, this is connected to this. We don't have this routing for multi-agent systems, so which agent to call, these kind of things. Mentioned we don't have sustainability aware routing, and what is missing is also the multimodal LLM routing. So every solution is only taking into account the prompt and not the images or the sound or any other multimodality. There is by VLLM, there is some multimodal. I didn't try, but they claim they have the multimodal model. Or of course, there is some data sets, they have the multimodal text, audio, and video, like this MEL data set. So it's quite interesting for a future research to have this kind of multimodal LLM routing. So this is everything I had to present. I hope you like it. You have just the bullet points of the summaries. I will not read them, and you have some of the resources which were used during the presentation. Thank you.